Boeing, India. Today we have an interesting topic for today's PDP session. It is about controller selection by Professor Omkar Sir, Chief Research Scientist from Indian Institute of Science. A quick introduction about Professor Omkar Sir. Dr. Professor Omkar Sir holds a rich experience in satellite image processing, UAV, nature-inspired algorithms, biomechanics, and also yoga. His research includes satellite, UAV, image processing, flood disaster management, and yoga. And he has also developed several algorithms and used them for various applications like road extraction, flood assessment, crop classification, crop growth analysis, radiation monitoring, etc. And his research also includes composite design optimization using nature-inspired techniques. That is really a wow factor. And Dr. Omkar Sir is also a celebrated practitioner and a teacher of yoga. He has been awarded for his various contributions, and he holds the Satish Dhawan Lifetime Award for contribution to the field of image processing, Grand Challenge Award from Karnataka Biotechnology and Information Technology Services, Eminent Engineer Award from Institution of Engineers Karnataka, a 2024 Top Scholar Worldwide by Scholar GPS, and he has also been recognized for his yoga works, and he has received Karnataka State Rajyosava Award from Government of Karnataka and Kempegoda Award from BBMP for his contributions in the field of yoga. There are a lot of things to say about Professor Omkar Sir. I'll not take much of your time, and it is very proud and glad that we have Omkar Sir as part of our AeroTHON 2025. And I would really thank him for taking his time in this busy schedule and sharing his knowledge on controller selection. Thanks, sir, for accepting the invite. And I will hand it over to you and hope the students who are participating in this PDP session will have a great learning. Thanks, everyone. Over to you, sir.
Namaste. Thank you for the nice introduction, Chaya. And now, I will share my screen. All right. What do you want? Optimize for motion and video also is there. Should I select this? Entire screen. So as I share, I think, Okay, do you see this?
Yes, sir, we are able to see.
Okay.
Others, can you please confirm?
Okay, so are you seeing my?
Yes, sir, it's visible.
Okay.
Yes, sir.
Yeah. So, well, I will be talking about controllers, but essentially we call it as drone computing because it's all about what you compute on board the drone. So I happen to head the 3 labs, and then I work for Department of Aerospace Engineering, IASC. I also happen to be the chairperson of Drone Standardization Committee in India. So this is about my drone connection. So this talk is more generic in the sense because whatever we talk about controllers, what is even now, what is ruling UAV is all PID only. So there is not too much to talk about PID. I will towards the end of my talk, I will bring something about PID. Otherwise, generally what is happening around the world in the recent past, and maybe look at some historical perspective of how these control algorithms came up. And in between, I will also flash some of the work that we are doing at our lab with regard to drone NGC, that is navigation, guidance, and control. That will be the organization of the talk. Yes, our lab is one of the oldest academic lab. It was inaugurated by Ratan Tata. This is how we would represent drone these days. It is the Garuda and Vishnu. Garuda is the carrier of Vishnu, the air Garuda. So Garuda represents the drone in its true sense of flying. Narayana is the abode of knowledge. So today, drones are getting embedded with artificial intelligence. There are a lot of things happening with regard to that. So that's how I've chosen this to pictorially represent the current status of drones. Well, we will go back to, because this Operation Sindoor has changed the whole perspective of drones itself. Now there are a lot of moves. We are also part of a lot of meetings where we are trying to look at the whole drone industry in a different perspective. May 2025 Operation Sindoor. What happened is India executed coordinated precision strikes across 4 days, emphasizing on control of escalation and clear political intent. We all know what happened. And BrahMos was used along with Su-30, which delivered the effects. Layered air defense tank, the S-400 in the Akash, kept the air picture stitched together and under this electronic warfare pressure. Today, this has become a big thing, electronic warfare, EW. So a lot is happening in the country about how to cater to this EW, how to create test beds, because there are a lot of lessons learned during the recent conflict, and they found that many of our UAVs can easily be jammed, and many UAVs had problem. But anyway, the lessons were immediately learned and circumvented, and successfully the UAVs have been used. It matters here because the win was not just hardware, it was control, timing, deconfliction, and resilient links. So guidance for autopilots could do their job when GPS and radios were contested. So this is a very, very important thing, because we came a long way to achieve levels of ATOL, that is automatic takeoff and landing. It could go anywhere and come back, but we thought that GPS is the sacred guard which will protect, but now we have understood that it is no longer so. If GPS drops and radios get noisy, what to do? That's a serious thing. So now controls does not necessarily simply limit to what kind of algorithms you design, whether it is PID, or tomorrow you can put some LQRs, or maybe some model predictive or adaptive controllers, whatever, including neural network controllers, whatever you put, ultimately how robust it is, that will become the question. So now we have reached a stage where we have to look at this so-called cyber security along with our control algorithms. They cannot be seen in separate phases. So control means a system repeatedly measures itself, compares that reading to a goal, and then corrects its behavior to stay on the target. Of course, this is very generic. We know it is true for any system, be it be missile or a drone or an aircraft. The same feedback pattern powers everything from thermostats to drone. Although it started one of the earliest controllers, if somebody wants to name, it is the thermostat. So this is one of the earlier example where Connolly's Drubble's self-regulating oven, going back to 1620s, which automatically adjusted heat with a simple feedback mechanism. So this thinking sensor, controller, and actuator keeps design choices clear when missions get chaotic. So in all these things, so this basic infrastructure was known to humanity as long as the 1620s itself. Now the outcomes you can see, it is not just the warfare. See, jamming and spoofing spoofing flood the air. Resilient guidance keeps mission on plan. So we have seen in Ukraine and Israel, everywhere we have seen now. The battlefield shows how EW degrades links and GNSS, forcing drones to adopt hardened guidance and autonomy. This is very important. Now, designers counter with sensor fusion, stricter integrity checks, and alternative um, navigation when satellites become unreliable. So there is a whole lot of things that are happening, starting from PQC, that is post-quantum crypting, to inertial navigation systems. Well, this is not just the war that is going on. You can see the zip line, beats distance and weather to deliver blood in minutes. This has happened. National scale programs proved reliable. Fixed wing autopilots can cut delivery times and reduce wastage for critical emergency medicine application. So many parts of the world, this has become a reality. So even there, you see, although it is for a peaceful purpose, yet it needs to be addressed. Then fly-by-air protections keep pilots from over-controlling at the edges of the envelope. The envelope protection logic minimizes the risks of loss of control events and has shown statistical safety benefits over decades of A320 family operators. So that figure, what you see, I've expanded. This is just to show what are the factors to be considered to decide normal flight envelope. Well, 1620s, if you look at the double self-regulating oven, it's one of the earliest documented feedback devices in the history. It was very simple. As the oven grew too hot, simple mechanism closed the air path. As it cooled, the path opened again to restore the set level. So this is the same control loop idea we rely on today also. So since the state compare to a set point and correct automatically. Early thermostats taught engineers that stability depends on how strongly and how fast you correct errors. See, stability came little later. The feedback, they thought, then they could see that there could be sudden jerky reactions. Now, that's when they wanted to talk about the stability. Same thing with respect to the Christian Huygens built the first pendulum regulated clock. This is way back 1656, transforming the timekeeping accuracy. So the pendulum's steady swing acted as a natural governor, turning irregular gear motion into precise ticks. So this leap enabled dependable navigation and science, showing how stable oscillations make control practical. Because without stability, the controllers would be practically useless. So this is one of the important milestone that has happened. From these, the control theory marched towards team governors, stability tests, and eventually fly-by-wire. So this is where, if you look at the historical development, this is how it has happened. Then we know this is a very famous uh, fly ball governor from James Watts, automatically throttled steam to keep engine speed steady as the load changed, introducing industrial scale feedback control. So this mechanism used the centrifugal force. The concept is very simple. As speed rose, the ball flew outward and partially closed the throttle. As the speed fell, the balls would drop and the mechanism would open. So that's how it controls. So engineers soon noticed some governors hunted speed oscillated because the corrections were too aggressive or too slow. So next milestone is on 1868. James Clerk Maxwell analyzed why governors oscillate and how to stabilize them, planting the seeds for modern control theory. So this is how the development today we talk about these theories. In 1927, Harold Black invented the negative feedback amplifier, feeding a portion of the output back to tame distortion and stabilize gain. Then you have 1934, in his paper, he explained how feedback could turn noisy nonlinear tubes into precise building blocks if you accept reduced raw gain for clean, stable behavior. Then in 1945, it is Hendrik Bode then gave engineers practical tools. Today we talk about these Bode plots, gain and phase margins to shape loop gain and guarantee stability. That's very, very important because of these early inventors. They could see that without stability, this would be of no use. So uh, the tools got developed, and unless you have a good analytical proof, you cannot depend on it. For example, we have been talking about neural network controllers maybe from nearly 30 years, but even today, not many dare to put it on any of our aircraft where man is in the loop because they lack this kind of analytical stability proofs. Well, with all these things, when the so many data is available, we knew that redundancy is needed, and so many sensors will be there. Then how do you get a good estimate? What is your confidence in the sensors themselves? This is where the Kalman filter came into existence, uses noisy sensors to estimate the true state, weighing each source by how trustworthy it is at that moment. So NASA adopted this Kalman filtering in the early 1960s to support Apollo guidance and navigation, turning jittery measurements into reliable trajectories. Because when we talk about feedback from various sensors would come. Now we need to have a good estimate. This is where Kalman filter and several variants of course, Kalman filter came. And even today, that is what is sitting in all our controllers. I'll show you towards the end of the presentation. So this was the leap from many shaky readings to one best guess every fraction of a second. So this was a very great milestone. The same principle powers everything from cruise missiles to the IMUs that are sitting on our mobile phones. So everywhere, this Kalman filter has become ubiquitous in estimating the states. Then it came to fly-by-wire to fly-by-thought. Fly-by-wire, we have all heard of it. I did put fly-by-thought because we did one such experiment where we could fly the drone by thought. I'll show you that. So in 1972, NASA's F5 digital fly-by-wire program uh, proved that computers could stabilize and control aircraft with reliable redundancy. In the left, you see how it was. You can see the number of switches and display. Vis-a-vis on the right side, you have modern airline cockpit with envelope protection callouts. So you can see how much of complications have been addressed by this fly-by-wire. So this replaces the heavy mechanical linkages with sensors plus computers plus actuators. So this question of integrating the sensors, computers, the associated algorithms and the actuators, improving the responsiveness and safety. Modern airline added envelope protection, preventing pilots from commanding dangerous attitudes or stalls while still honoring the intent. So these ideas directly shaped UAV autopilots um, even today. So we are doing that's how we now are reaching, at least as far as the PID autopilots are concerned, we have somewhere reached quite a stable flights. So this is what I was talking about, fly by thought. So what we did, this is the work done by us in our lab at Department of Aerospace IISc. The whole idea is you have these EEG headsets. We could get on a pocket headset which has 14 channels. You have to wear it and you must think. We could only generate 4 distinct commands: right, left, up, down. So whenever we think, or generally most people are always thinking, so there are a lot of electrical activities in the brain. Some of them will reach the skull, surface of the skull, and these are the gadgets that could pick up those electrical signals. And this is a wireless headset. Through Bluetooth it will transfer to the ground control station, the computer, where you can analyze those signals. So you can see bottom down, the signals look very crazy, but even in that, you can pick up the right features if your signal processing is good. For example, if you are thinking only about the direction right, some signal would show up that okay, this fellow is thinking about right, and you can pick up that. Similarly, if you are thinking left, not gesturing, no uh, voice, nothing, just thinking, little focus is of course needed. Similarly, left direction, if you are thinking, one of the um, signals would become dominant. You have to pick up that. Similarly, up and down. And once you can do that, then you can transfer it to the drone firmware. So that is what drone is going to understand, and you can move. So this experiment also we did. So this is our quadrangle where we took one drone, we implemented. You can see the drone flying there, and I'm sitting there on the chair. There's no hand movement, no gesture, no voice. It is just through the thoughts we could move the drone to right and left. Right and left movement was very easy. Up and down, we could achieve most of the times, but still that was a little shaky because this is only a 14 channel headset. But later we could not really carry forward this work too much because we wanted a more sophisticated headset. Today, this kind of headset with 255 channels are also available. But anyway, they are expensive and it needs to be explored. So, but this is a possibility. This can have a lot of implications in terms of driving the drones. So these things have also been used for civilian and societal purposes. In the flood in 2018, one of the worst floods hit, and reliable hover or position, hold, and return to home behaviors made small UAVs useful for scouting routes, and finding out who are all held up in any situations. National disaster records show the broader response involved massive multi-agency coordination, where quick aerial perspective shortened the time from sighting to rescue. Because as you know, during these periods, any kind of satellites would also be futile, because if there is a cloud cover, optical sensors don't work, and only thing is we can rely on SAR images, but they are not very clear. In fact, we have done elsewhere in as a part of one of my PhD students, we have done how to do flood detection using even SAR images, but there you cannot use actually to identify the humans. That would be too much. UAVs is the best bet today, because all weather UAVs are possible. One could fly. So um, we have developed algorithms where this is work done in our lab, where you could identify how many people are caught up anywhere. You can have the tag of lat long location there, and we have also trained this is based on machine learning, and you can also identify any other animals that are caught up in the flood, where how many, which category of animal is struck, we can easily identify, so that the rescue authorities can take appropriate decisions. Then this is about the other places where controllers play a vital role. You can look at this KMAX unmanned cargo load swing clamping. A 2013 mishap investigation highlighted how tailwind and suspended load oscillations can overpower controls, reminding designers to plan routes, limits, and damping with payload physics in mind. Because today, a lot of such applications are there. It need not necessarily be military applications, even in emergency evacuation, etc. This kind of what you call as the sling loads become important, and things have to be addressed. So the USMC's unmaxed KMAX helicopters proved that autonomy can remove trucks uh, from IED prone roads, that is explosive prone roads, flying thousands of resupply sorties in Afghanistan. They have done. Then the night ops across a nearly 3-year deployment, the two airframes lifted over 4.5 million pounds of cargo, food, water, and ammunition, largely at night and in rough weather. Well, the lessons learned here are definitely useful for UAVs also, because in UAVs also these kind of sling loads are going to be common, because UAVs now of bigger categories are coming up. For example, you want to save some survivors anywhere, be it be in some sea or some building top in the disaster prone area. So these sling load operations are important, and the related physics have to be properly understood. Then zipline, today it has made big civilian impact everywhere. Um, Rwanda's partnership with Zipline, as in Africa, built the world's first national medical drone network, turning hours of long road runs into on-demand flights in minutes. And such kind of experiments are also happening in the northeast of our country, India. I think the Red Wings is a company. I know of them, and they have done several sorties to provide emergency medicine services in Northeast. Reduced wastage. A peer-reviewed 2022 Lancet Global Health study found faster delivery times and a 67% reduction in blood unit expirations after drones came online. So because they have some limited shelf life, so that is the worry actually. In fact, that is one of the biggest thing. So drones could be of great use there as well. So when we say these things, we should remember always that even in emergency medicine service means you cannot always wait for a very great weather and then fly, because it's a requirement, life-saving requirement. That's why very robust control design becomes very, very vital. At the same time, we should remember that when we say that if it is uh, if it is not protected in a right way, then anybody can attack and spoil the whole mission. Therefore, cyber security, controller, how do you handle communication, they all become very, very vital. Distribution centers, results at scale continue. Reporting indicates a large share of blood outside uh, Kigali now moves by drone, with parallel expansions in Ghana and beyond. So there's a whole lot that is happening, and the whole scenario would definitely change. It won't get limited only to emergency medicine service. Why they are doing now experimental emergency medicine service is because even in our country, we have not cleared the BVLOS operations yet. That is, beyond visual line of sight operations are not cleared, but case by case basis, the DGCA would clear them. But by and large, as a policy, it has not come into force because of various concerns, because our country has a lot more challenges in terms of density population, so how to create corridors, how to handle this UAV traffic management, UTM, is becoming a serious question, whether we should create appropriate air corridors for these things and where to create, and what is the reliability of these machines, and the legal issues that could come up. So all these things are being discussed. Well, when we do this, we all remember the 737 MAX story. The maneuvering characteristics augmentation system MCAS was added to make 737 MAX handle like older models. It automatically nudged the nose down if it believed the plane was at risk of stalling. So MCAS initially relied on data from just one angle of attack sensor. So if that sensor failed and gave wrong data, MCAS could repeatedly push the nose down without pilot input. You can imagine the situation of the pilot in that case. So in two crashes, Lion Air 2018 and Ethiopian 2019, faulty AOA readings triggered MCAS repeatedly pushing the nose down, even when the plane was not stalling. Pilots were overwhelmed and could not stop it quickly enough, because once it is on autopilot, the pilot mode will be different. So what changed? Boeing updated the system, so MCAS now uses data from both angle of attack sensors. So this is where redundancy becomes very, very important. But lessons have been learned in a hard way. But anyway, one cannot brood over what went wrong, but we should learn lessons. So this is very important. Even in UAVs, this is very, very important that you should have the redundancy. So we have seen this when the US RQ-170 was captured by Iran, that the US is a stealth drone. The Iran claimed that they jammed its link and spoofed its GPS, so it thought it was returning to base and landed intact in Iran. But anyway, US had a different opinion. Whatever it is, so this shows that this kind of uh, technical decoying is reality, and our drone someone else can actually spoof and get hold of it, And especially if you are collecting some sort of um, important data, you know, because we do, obviously, when it is a spy drone, we would love to record what we want. And now all that is a question. If it is captured, whatever we have recorded, and that could contain any other uh, data of the country, that would become a serious issue. So now a lot of things are being how to record with the proper encryption. So there's a whole lot of things that are happening. So GPS denied navigation. So in cruise missiles that has come, classical cruise missile like the Tomahawk proved GPS-free precision by matching terrain contours and comparing camera scenes to stored maps. The autopilot reads radar, altimeter, terrain profiles en route and then uses scene correlation near the target to refine the aim to meters. Because as it approaches, it will see as the window of the whole scenario becomes smaller. So that is the trick. So the concept is a template for GPS denied UAVs today. So we are also looking at how to use some of the vision based techniques. Navigate by what you see and feel, not just by satellite. Because GPS in a critical situation, GPS, either someone else can manipulate the enemy or the GPS operator himself can just turn off the signals, in which case it is a very dangerous situation. Therefore, this kind of what the technology that is already being used by missiles could be, not could be, is already has become a template. We have also done some small work in this direction of vision based uh, navigation, which I'll show you some results later. So these are the two very well-known things. Jamming drowns the signal with noise, dropping command links or GNSS log, especially near conflict zones. Recently, in fact, in this very Indo-Pak Sindoor war, this has come to the experience. So implication is designed for loss of link autonomy. Then spoofing transmits believable counterfeit GNSS, so receivers compute the wrong position and time. So implication requires integrity checks and cross checks. So this is where zero trust architectures, even though the signal is coming from your own side, you cannot trust it. You have to validate everything that comes. So that zero trust architectures are on board today. So without GPS, you have the visual inertial odometry, VIO, a camera plus IMU watch how scene moves to estimate your position locally. Great for indoors, under bridges, urban canyons where GPS is weak. Works today on PX4 or autopilot. You just feed VIO or optical flow into the estimator. So it's already there on our plate. And even much before this, we did some work. I'll show you. Then terrain and scene matching. The above, the drone compares what it senses, terrain height or camera image, to a stored map and follows that match. Classic cruise missile idea that does not need GPS for route and terminal guidance. So that is being utilized even in drones. Best when you know the route and can preload good maps. And in most of the cases, because of our good uh, satellite imagery, we can get to know wherever whatever enemy targets you want to aim, you can get it from the satellites. So good images, high precision images today are available. So this is a very much plausible technology. Another is the beaconing plus alti sensors, where UW beacons in a room give short range fixes, barometer plus rangefinder study your height. Pick this for warehouses, labs, where you can place anchors. Then magnetometers help heading but need careful placement and calibration around metal. Because we have seen that when you are using magnetometers, recently we had this experience. We gave one of our, because now I'm also going to show you one of the companies that uh, I have incubated at IASC to make IMUs. We had supplied and to test it on a drone. Uh, they had put it on a fixed wing, but for some reason they put some SS screws, that is stainless steel screws, very close to these IMUs. So its behavior was changed. We also first did not understand. Then when our team went physically there, they could see, oh, this is the problem. They have put, because the ferro content in the screw, and that could affect the magnetometer. So when you use these kind of gadgets, we should also take appropriate care of how to mount, where to mount, etc. So this is something that we have done in the lab. Imagine a situation like heavy traffic. Of course, it also has military applications. So we made our own small UGV, and there is a QR code. RQ markers there. So drone has a down-looking camera, and we expect, okay, if it is on the ambulance, and if it is stuck in the traffic, ambulance driver can trigger the drone. It can go upstream, police alert him, and as the ambulance moves, he should also able to come and perch on the ambulance. So that we have developed our algorithms which can do that. Next is this, of course, obstacles, non-availability of GPS. So far we have discussed. So what we have done is, we have not tried any sensor fusion or anything. We have come out with a very lightweight algorithm and with a monocular camera, and we have used the process flow where feature vector for each window comprises of 11 loss and 15 Harris features. Here what we do is, um, we divide the windows into some strips and then use the linear regression learning, and you can see the result. It can move. Right side shows how the computation. Inside the IAC, we have a good greenery, we have good tree area. So it is autonomously moving from point A to point B, which is configured earlier, and it avoids all the trees. So this is obstacle avoidance, GPS denied. But the problem with this texture-based learning is that when you have, if at all you have a solid horizontal branch, this might fail. So we looked at the optical flow algorithm. So this is what it is. Optical flow. I will not bore you with too much of these descriptions. And this is what it is. With optical flow algorithm also we tried, and it can do this obstacle avoidance very smoothly. So this is how it moves through the woods. Of course, this is the initial algorithm, because this is just on one Android board we have very lightweight algorithm. So not very sophisticated. Now we have learned a lot of lessons, and of course computing platforms, real-time computation, they have also improved. And this is another thing that we do when you have pathways like this. For example, a military convoy is to go. They don't know how the pathways go in the jungle, and there could be some IEDs or explosives on the way. So the best way is they can send a drone, and the drone has to detect the path by itself and travel and can send the video feedback to the ground control station so that the army can safely move forward. So this is what we call as the path following algorithm. Here we used convolution neural network model in the machine learning architectures. The training data we used actual flying plus from the games of the sports. You get the car racing games, etc. That training data also we could use because there's after all moving, in different contours. We did use and we tried it out, and we could get this flying. This is the IIC road. It's only as the path following, it will detect the edges and center itself and fly. And it's going at about 40 km per hour. Okay. So now how we fight back is that you need to really, to take care of this. You have the FHSS, that is the frequency hopping spread spectrum, and direct sequence spread spectrum makes a jammer's job harder by hopping or spreading energy. So a single narrowband interferer can't knock out the whole link. This is one approach. You can have multi-band plus autonomy, multi-band, multi-path radios with smart loss of link behaviors, keep the vehicle flying safely when one path dies. Then you have the controlled reception pattern antennas. The anti-jam antennas uh, steer nulls toward jammers and gain toward satellites, preserving position in noisy strikes. Then last resort is the fiber. Recently we saw this fiber optic control, which bypasses all these spectrum energy, and it has its own limitations, but no jammer can do anything for this. So this is what it is. Recently, Ukraine, very recently, it has used the wire that cannot be jammed. Fiber optic drones carry a thin cable from operator to airframe, creating an unjammable low latency control link that shrugs off RF jamming and spoofing. Units report precise terminal control for last tens of meters because commands and video never touch contested spectrum. It is direct. I mean, it's a physical link. Trade-offs, of course, are real. Snag risk. The optic fiber can snag anytime. The drag penalty on the flying vehicle, and path planning constraint, because when you want to run the fiber, you cannot have too many turns and twists and obstacles, etc. So, well, they have used actually, so it has worked. And even in our country, there are moves, at least in some known pathways. This would be a wonderful vehicle to hit some very targeted um, point. One could design, one could get the roadmaps and use them. So essentially, yes, switch to VIO or optical flow. We have shown a couple of examples when the GNSS is not available. Then constrain motion, constrain speed and acceleration to keep visual features in view and maintain estimator health. Then climb only if texture improves. Climb only if texture improves. Bare roofs can be future proof. If jamming persists, be ready to execute a RTL or land fail-safe policy? Well, the quantum is trending now, quantum computing. So we have all the way from the post-quantum crypting that is there. NIST has finalized the post-quantum standards, and recently we all met in the sets at Chennai. Now that is a office under the Principal Scientific Advisor's office to discuss some of these issues. So I think even in the country, this is going on in a big way. That how to do quantum key distribution also, which is promising, and also post-quantum crypting, so that your mission is not easily tampered by the enemy attacks. Well, now we will just look at the controls very quickly. A control system measures what is happening, compares it to the goal, and corrects itself to stay on target over and over many times per second. So this loop is called feedback. It works for thermostats, drones, rockets. Only speed and complexity change. Feedback matters because real sensors are noisy and actuators have lag. Without feedback, small errors can grow into oscillations or drift. This is all well known. So in practice, we organize things as sensor, controller, actuator, then check if the response is stable, fast enough, and accurate for the mission. So that's how the concept of inner loop and outer loop has come, and why we stack them. This cascaded design is fundamental to robust flight control as detailed in the documentation from the most popular architectures, PX4 and Autopilot, which all this the most of us use. We layer loops so slow, high level goals, position and velocity, speed faster, lower level loops, attitude and angular rate that motors can track cleanly. So inner loop is the fast stabilizer, rate and attitude, running at hundreds of hours to knock down guts and motor nonlinearities before they become visible. So for stable flight, this is very essential. The outer loop moves you where you want to go, position and velocity. That is at a slower pace, um, handing set points down to the inner loop each cycle. So this is very understandable because what has to be fast enough to maintain stability and what can have little slower to ensure proper navigation. So both PX4 and Autopilot implement this cascaded design. PX4 documents the chain and control allocation explicitly, while Autopilot's libraries pass desired angles or rates down the stack. So this is the brief overview of the stack. Two kinds of loops. Outer loops decide where to go, position, velocity. Inner loops keep the drones instantly stable, attitude and rate. The outer loops send set points down each moment, while the inner loops run much faster to swat gusts and track commands. Um, Both these PX4 and autopilots use the same pattern, and we know that both are open source. So tuning rule of thumb: start inside out, rate, attitude, position. Auto tune both stacks, focuses on the inner loops first. Inner loop because we need it to be quickly stable. So they carry the same DNA if you compare both the PX4 and autopilot, and incidentally, both rely on EKF for state estimation. And practical differences: PX4 defaults to EKF2 and lets you switch estimators. It also ships an auto tune that targets the rate and attitude controllers first. Autopilot EKF3 supports multi-lane sensing with in-flight lane switching and sensor affinity, and offers an auto-tune workflow with clear pilot knobs. Um, so essentially that is the difference, but largely it is PID cascaded loop EKF. Some variations are there. So we know this PID, what P does, I does, E does. Um, for the for the kind of audience I have, I don't need to emphasize these things. But still, P reacts how far you are from the target. It is the main push that closes most of the gap fast. I is cancels the lingering bias by accumulating small errors, but it must be bounded to avoid wind up. Then D anticipate change by responding to the error slope, damping overshoots and smoothing motion. PX for an autopilot use PID for the inner rate and altitude loops. EKF state estimation, this is another very important thing. The extended Kalman filters gives uh, the robot or a drone, whether UGV or a flying drone, one best guess of the state, position, speed, accuracy, blending multiple noisy sensors. And single sensors are imperfect. We already seen the case study with the um, 737, what happened. So we need to have multiple sensors, IMS drifts, GPS jump, barometers wander, cameras lose features. Combining them is better than any one alone. So this is where Kalman filter estimator is very important. Drones and robots must update the best guess many times per second while moving. So how it works? Predict from the last state, use physics uh, to predict where you should be and how uncertain you are. Measure, read the different sensors, compare and weight, compare the difference between the prediction and each measurement from the innovation, and weight them by trust, noise or uncertainty. Then clean consistent sensors pull the estimate more, uh, and then correct them. So blend into a new best estimate. That's very important. So the IMU is fast but slowly drifts when you can take the drone. GPS is absolute but noisy. Baro is good for altitude. Vision helps indoors. EKF uses them so the drone flies smoothly. When GPS is clean, it corrects IMU drift. If GPS drops or glitches, EKF leans on IMU plus borrow vision until GPS looks same again. So that is the power of the EKF. And we have done, of course, we are going to just next week we are presenting it in a conference, um, how to automatically tune this PID by using the um, reinforcement learning, that is the a critic reinforcement learning we have done, and we trained and tested extensively in simulation across diverse flight paths including hover, circular and square trajectories, stretch system with variable payloads, mass changes mid-flight, and introduced realistic Gaussian sensor noise for messy measurements. monitored altitude and attitude tracking alongside learning curves to ensure rapid stabilization and consistent course maintenance. The outcomes were compelling. The PID maintained the predicted control while the auto-tuner seamlessly adopted gains in real time. So this is a paper. If some of you are interested, we can share this paper. And of course, just to emphasize again on PID's role, a sudden gust swats the multi-copter during takeoff. So what do you take first? Crank P, increase the proportional gain to respond more aggressively. Then add D, increase derivative gain to dampen the oscillations and improve stability. Rely on I, increase integral gain to accumulate and correct the errors. So that's how you can do this. So from Sindoor to campus labs, build one loop well. So tune inside out, practice GPS denied safely, test fail safes on purpose. This is way to do. In fact, we have been telling Government of India to establish a EW test bed so that drones could be tested. So this is something we have done in our lab. We have used this for agricultural drones. You know, agricultural drones are the most popularly used drones commercially among all other types of drones. This is the one which has taken a big lead. And even in that, we have seen from the IFCO statistics that out of about 1,000 drones, 500 drones have crashed because the pilot could not avoid the obstacle. So we have done this obstacle avoidance. I will not go into the details. We have used a omnidirectional radar and developed the algorithms. I'll not go into these details. We have applied for a patent. A patent is pending on this. So what I'll do is I'll go to the result. So this the pilot goes and you see that blue wall. So even when you want to go close to the wall, and even there if you give some pitch up command, it won't go. 2 meters away from the obstacle, despite forward pitch input, the drone does not move forward. You see, you can see the left side what we are giving pitch up. Now we do the pitch up. See, when you do the pitch up also it doesn't go. So this algorithm is what we have done in the lab. Then this is another interesting thing that's happening. We have made a company called Yanendriya, where our team is working on the inertial navigation system. And here we are trying to overcome this GNSS limitation by using the INS, inertial navigation system. And we have tried various things using radar-based SLAM, for example, for indoor, etc. This is building the SLAMs would become very easy. Using IMUs, then we also made the visual odometry navigation system for UGV, outdoor. So you can see how it closely takes. You can see the right side graph, left side is actually the drone moving, and you see the camera mounted on the, sorry, not drone, it is a UGV. Fairly good accuracy. Now this is the flight controller we have come out with, and it compares well with the PX4 and autopilot. Some units we already got the order, and I'll show you a flight based on this. So this is from our Made in India autopilot. I just wanted to observe when the pilot even pushes this, it's able to stabilize very quickly. So see now he does that. See, but when he does that, it stabilizes very, very quickly. And we have been able to produce them at cost comparable to the Pixar Orange and such variants. Be able to stabilize it, will see how stable it is. Look at the response of the vehicle. Yeah. So all in all, the choreography wins. Missions succeed when people and machines move in sync under pressure, letting low-level loops do their jobs even under electronic warfare. Life's not just wars, it's not just for military purpose, it's also for good use of the humanity. Fly by sight, and so we should be ready to have on these kind of facilities. But now we are talking about SATCOMs also, but yet this is very, very important. So the link is everything. We should not lose the communication link, but be prepared to do that. Jai Bharat, Namaste. So if there is anything, let me know. I think I should stop sharing then. Okay, that is from my side. Thank you for your time.
Thank you, sir. Thank you so much. Sir, one second. One team member has raised their hand.
Yeah, please, please.
Kindly unmute yourself and ask your query. Rohan?
Here.
Yeah.
Sir, thank you for the presentation and taking us forward to this valuable information.
Thank you,
Uh,
thank you.
First of all, we as students, we are using open source firmware like Autopilot and PX4. The GPS data is mainly being fetched from SRTM data, SRTM1 and SRTM3. So SRTM data is again not too much reliable if there's a topographical change. Mainly we can have it in border areas where some border road organization comes and topographical changes. In such situation, there's a need to have an external, like as you said, a monocular camera or a depth sensing camera to be integrated. So in that fashion, where can we find that learning of integrating all these sensors? Whether IIC is providing any sources to.
Oh, yeah. Please, please. We will
Yeah,
help you, no problem, because we have already done in our visual odometry, we have fused all these optical with IMU, etc. In
yes,
fact, I didn't bring that presentation. You reminded me, but somehow recently one of my MTech student did the same thing,
yes,
and that paper also we are presenting in the upcoming conference the following
yes.
week. Should be able to help you. Yes.
Sir, one more last small doubt, sir. If SRTM data is being imported by the mission planner or any ground control station, why can't our Indian satellites data be imported so that it can give more reliability rather than going for this approach?
Yeah, I think the pathways are getting open. Now
Yes.
SATCOMs are now slowly opening up.
Yes.
Thus far it was difficult, but now I think the situation will improve because of the requirement.
All right, sir. All right.
So I think it will happen.
Sure, sir. Sure, sir. Sir, please share us the link about the SLAM methodology and all those autonomous navigation-based navigation.
Some of my papers are there, or if you need anything specific, you can write to me, omkar@iasc.ac.in.
Yes, sir.
I'll connect you with my students.
Yes, sir. Thank you, sir.
Teams, do you have any other questions? Please raise. I think no questions, sir. So we will finish the session, sir.
Okay, thank
Thank you,
you.
sir. Thank you so much, sir.
All the best.
Thank you, sir.
Namaste.
Thank you all. Thank you.